Welcome, organic students, to the last section where we have a functional group as the topic title. So from here, we're trying to expand upon bigger picture things. So this is our last functional group to cover, amines, and we have done a lot. It's a good time to reflect and see, just appreciate all of the functional groups. You've learned how to react and form and their relationships between them. So these are kind of organized by types. So we have our CC multiple bonds here. We do addition reactions with those, right? We did our electrophilic aromatic substitution or nucleophilic aromatic substitution here. And then here's our oxygen functional groups. And so acid base usually SN1, SN2 for our alkyl halide, ring opening epoxides. A lot of that's organic 1 stuff, but we try to bring it back in. Thiol sulfides as our analog of these, right? So similar behavior, but disulfide has some really particularly biochemical importance. And then, of course, our beloved ketone, our carbonyl section, starting with ketones, working our way through amides, acid chlorides, and hydrides. And then I ended it on several nitrogen-containing functional groups because, yes, we are focusing on amines. Now, we've seen amines many times. We've made them from amides, right? Nitros, and those will be touched on as review here. Also from nitriles and imines and amines, but we can't help passing through some of those intermediates because they are sort of all interconnected. So because you have covered so much ground with functional groups, you really are ready for what's called a total synthesis. So where there's a difficult target and you do functional group interconversions or carbon-carbon bond forming reactions to expand the molecule and enable you to actually build up your carbon skeleton. So I'm going to lead with one as an example to make you ponder. I have it separate document as a workshop, so you could feel free to get that one. So let's introduce this one first. So physostigmine is a natural product, and that's a challenge that we have, not seen this kind of molecule to have to make in this class before. But for the total synthesis chemists out there, the natural product chemists, where they aim to synthesize something that is a natural product. I'm going to pause. I think my cat's howling again. You've seen this before, so I apologize. I'm letting him in. This is how he likes to be held. And I guess I'll let him down now. See if he wants to stay in here now that I've actually picked him up. He's got his own agenda. Okay. Last time he went to sleep. We'll see if that happens. Okay, so back to physostigmine. This is a very challenging natural product, and when you are the first to synthesize it, that's celebrity status in the chemistry world, and especially in natural product synthesis. So there's celebrity status kind of attained with the first to synthesize a difficult target, which this was one that they kind of compete. It's almost a race. They don't want to get scooped, which means someone figures it out before them. So the first synthesis for physostigmine is credited to Percy Levon-Julian, and look, we're coming up closer to our time period. A lot of the stuff you learned was back in the 1800s, but now that we're doing more complex stuff, you're going to see more recent examples. And for Percy Levon-Julian's work, he was acknowledged on a stamp. So all you stamp collectors like me out there, I really only collect chemistry stamps, but I appreciate a lot of the others. That's a good one to add to your collection. So and you can actually see on his chalkboard, same structure, right? He said indole ring, at least part of it. And so it's kind of a cool shot. Anyway, so yeah, you get kind of celebrity status for the first successful synthesis, and then there's usually another person who manages to get the status for the most efficient or shortest route. So those are kind of the two holy grails for those synthetic chemists. There's just a portion of the synthesis here. It's much longer, but just to kind of see, there's some recognizable reactions in here for you guys. And so, in reagents, we know about that, AlCl3. So I'm going to, and we know that very well. I'm going to leave this up here and return to it. So I'll leave this for you to try. Return to it, probably in a workshop format. But think about how you can at least get to a more advanced intermediate, and it's not all the way there, but you could see it form. You could see the additional ring form and everything like that. And some of the reactions in this actual section will help you, so that's why we'll do that again at the end. But that's how you really put this all together, as opposed to discrete functional group chapters. So to go back to to move on rather to our amine reactions, you're going to notice because we've done so many, some will be repeats, and I'll note that. But they're just worth bringing up so we don't forget they're there. And what really always helps, as usual, to understand the reactivity of anything is to pay close attention to its structure. So that'll help us predict how we expect an amine to behave. So for example, when we did the acid chlorides, we saw that that was a leaving group. Well, this is not a leaving group. We don't usually see amine act as a leaving group. We usually see it act as a Lewis base, which means a nucleophile or a Bronsted-Lowry base, right? So nuke or proton acceptor. So like we have been doing throughout the class, whenever we focus on one functional group, we think about how to name it. So let's name a simple amine with some branching groups to see how we establish priorities. So when you name an amine, we get the new suffix amine. And that's when it's the higher priority group present, like it is here. I'll make a little note here because I don't think I have it here. If amino or amine is lowest priority, which could happen but doesn't happen as often with simple aliphatic chains, carbon-carbon and hydrocarbon chains, the prefix is amino. That's on our nomenclature chart for your reference, but just good to point out, because this example I'm going to do is the more common, where we will see it as the higher priority group. So notice that the only functional group here is an amine, so we are going to end in amine. That's going to be our suffix. There's something else peculiar about naming amines, and you'll see why soon. I'll start naming, and we'll see why we have the necessity for this N, this capital N you might have seen. So I'm going to number my longest carbon chain as usual, and I'm going to have 1, 2, 3, 4, 5, 6. Now, if I went the other way, notice that I would have had 1, 2, 3, 4. So this was the correct way to number. So I'm going to have a 3 amino group, but it's an amine. So I'll have to put a 3 at the front or put 3 amine, right? 6 means hex. And I have no alkene or alkyne, so it's hexane. It's an hexanamine. So I can fill that much in. But as I read hexanamine, I didn't tell you where the amine was yet. The amine was at the position 3. But I know that amine could mean this, could mean that, NH, say methyl, for example, or RNH methyl 2, NH2 methyl. So that's, an amine can have 2 R groups, 1 R groups, or no R groups. So what kind of amine is that? I didn't actually tell you in the name yet. That's where the N becomes important. We have to say what's attached to the N. So the N has 2 methyls. So we say N, and that's 2 methyls, right? So that's 2 of the methyls. So we'll have at least dimethyl. But do we have any other methyls before I assign a di to it? So notice on carbon 2 and 4, I have more methyls. So it's actually a tetramethyl. We still add them all together. But we explain exactly where they are with numbers for the carbon chain, N's for the amines. All right, so let's get into that. So we have tetramethyl. We've worked that much out. Now, where are those methyls? Carbon 2, carbon 4, nitrogen, nitrogen. So that's where we get the N. 2, 4, N, tetramethyl 3-hexanamine. So if you're done naming and you know you had tetramethyl, but you didn't tell anyone where those tetramethyls were, you know you weren't complete. But there's no number assigned to the N, so we have to use N. That's as complicated as we're going to get, but if you had multiple N's, you'd have to do N primes, and that we're not going to worry about that. Just know how to name with one amine that it might have alkyl groups on it, okay? Okay, so just as review before we start pulling out some new ones, which will happen pretty quickly, our most common amine reaction is acid-base. We used amine like in ammonia, right? Acid-base reaction. So you see an amine, aniline, for example, and you see a carboxylic acid, you're going to do what we've been doing for a long time, grabbing a proton to deprotonate the acid. So you see your ammonium, right? And that's something we have to acknowledge that that's always possible. So it's an equilibrium, really, and our carboxylate. But we've also seen that amines can behave in our whole acyl substitution section as nucleophiles. Those are by far the more interesting ones now, because then we'll see how they can attach and stay attached, not just grab an H. So these are things we've seen. For example, acyl substitution, remember we have a leaving group here. And I'm not going to do this whole mechanism because we've already done it. I've already spelled it whole out in that section, but I'm going to say it out loud. Attack, open, close, kick off the chlorine, right? We're at an amide when we're done, when everything's all worked out. So we have to lose that proton on the nitrogen in the process. So we knew we can make an amide, right? And from an amine. So we know that transformation already. What else can we do with amines? We can actually use, instead of having to attack carbonyl, so notice it's attacking the delta plus on the carbonyl, it could also attack the delta plus on a polar bond, like an alkyl halide. SN2 reaction, right? So we can go attack. Nice primary alkyl halide, easy to do, right? Kick off the leaving group. So what do we form? Well, we're not actually going to be done. So I'm going to leave some space on the side. I'll show you what we form at the end. We can actually do this since it says excess. We can do this 3 times till we take over all the binding sites on nitrogen with a methyl. I'm actually going to write ME so we don't mistake those for anything else. So how does that happen? Well, when it attacks, we have our amine with 2 H's still there, and now it has a methyl and it's positively charged. But that ammonium is not going to stay in ammonium. Some more of the amine will neutralize it. So we can take our, I'm going to call that R NH2 from the starting material. And so it acted as a nucleophile at first, and now it's going to act as a base. Here we go. Now we have a neutral amine. But because we said excess, it's going to keep going because there's a lone pair that can actually keep reacting. So we're going to repeat 2 more times to finally remove that last H and then take up the last lone pair. And so we have an ammonium. So this is a trialkyl ammonium ion. Okay, so this is a useful reaction. We will get to it soon because we're making this trialkyl ammonium. It looks funny. It's a charged species. We're doing this, even though it's just a repeated SN2, because we want the consequence that's about to follow. So product from previous reaction, trialkyl ammonium. Okay, now if we subject that to a base, what we've just done with amine is we have made that a fantastic leaving group. And this is called, I'm going to put that up here. I'm going to put it actually right here because that's the starting point. Hofmann elimination. You might remember Hofmann product being the less substituted carbon that got the alkene way back when we talked about elimination. This is how to another way to force it. So what we've done here is, I'm going to write a note here. So you modify your amine. So you start with an amine, you modify the amine, and there's two features that you've changed about it. It is now a bulky leaving group, but leaving group. It wasn't a leaving group before. It's also a good leaving group. So it wants to leave. So that means you've set up your amine, which sometimes you think, oh, I can't do anything anymore. Amines, as we saw in that total synthesis, they're very common in naturally occurring products, very stable. But if you can convert it to a leaving group, then you can do some chemistry on it. So you make it a good leaving group, but not just a good leaving group, it's also a bulky leaving group, which means it's going to show selectivity. Steric hindrance will stop the more substituted carbons from getting accessed. So for example, if we're going to do an elimination now, let's remember what happens in elimination. If you have a base and you have a good leaving group, you can do elimination, right? How do we find out what we eliminate? We look for the carbon, the alpha carbon, with the leaving group attached. That's our leaving group. We find all our beta carbons, and then we draw on those H's, those beta H's. And we have to decide which H is the best one to pull off. Well, normally, we would follow Zaitsev's rule and make sure we pick the H that would leave the most substituted alkene, one of those two. However, because this is so bulky, it's interfering with a base accessing a more sterically crowded part of the substrate. So it's only going to go for the least sterically hindered, the external H, the one on the periphery. So exo to the ring. Your book also uses Ag2O. So basically, those are interchangeable. If you see base or Ag2O, that'll help you take off the proton and eliminate. So E2 is concerted, kick it off. So we get that more difficult to obtain Hofmann alkene. So that's the whole reason we're going through all this, is to get that Hofmann alkene that you can't get without discouraging the formation of the Zaitsev product. So of course, the leaving group was the amine, which is a very good leaving group, because now you have a small neutral molecule that just is easy to form. Okay, so should we remind ourselves about just a little summary? I don't think I have this later, so I'm going to do it right here before we do this example. Okay, so I'm going to get back to this example here, but I just want to summarize just as a quick reminder. This is one scenario you're used to seeing back from Organic 1. So if I just take that simple alkyl halide, where the leaving group is the single atom, not bulky, we get Zaitsev major. So this is E2. And that's because we have an unhindered substrate and an unhindered base. Okay, the other scenario you learned how to get a Hofmann alkene as major, but you had to modify your substrate to be bulkier. So let's take that, start with that substrate. Notice that that is much bulkier than what we started with. And then if you really want to amplify the yield of the less sterically hindered alkene, then you are going to have to throw in a bulky base as well. So one of the alkoxides that's got a lot of, even something bigger than the t-butoxide, that's got a lot of branching on it. So bulky substrate, bulky base gave us Hofmann. So in other words, instead of getting the internal alkene, we got the external. So that's just a quick review. I think I accidentally spell Hofmann with 2 F's all the time. So bulky base plus bulky substrate. So what we're doing here that's different, say, how is that different? Number 3, which is now we're taking a bad leaving group, an amine, and then we're doing the 2 steps that you'll see over the arrow. So 1, excess methyl iodide, that turns it into a good leaving group, to KOH or Ag2O. So then we get our Hofmann alkene as well. But notice we were able to get this one. We didn't have to have a bulky substrate. We had to have a bulky leaving group. That's very handy because then we were able to control this sort of setup to prefer that one. We didn't have to modify our substrate, just a leaving group. So this is also Hofmann from bulky via very bulky leaving group. The leaving group is so close to the proton that has to be abstracted that it has that big of an impact. Okay, let's do one more example together. Okay. Now, normally in E2, we have to do a Newman projection to figure out which carbon is going to have the anti-beta H. We don't need to do a Newman projection on this one simply because if we look at our alpha carbon, we look at our two betas, the one on the end, which is preferred anyway, thanks to our bulky leaving group. So if you see that, you do definitely go to Hofmann. Okay, so notice that we have this H. Now, the consequence of a Newman is you learn that if this is drawn in its usual sort of zigzag formation, the wedge has to be, if that's the leaving group, has to be anti to the beta H, which we can see that's true here. That's on a dash. Now, that's true here as well, but we don't have to worry because there's free rotation and any one of those would be anti at any time, so you could pick any one of those. And so if it wasn't here, you'd have to rotate until it was to predict the stereochemistry, right? So just that's a good thing to review because that comes back. But for this particular problem, this one's not preferred. This is the preferred one. So that actually makes it easier, right? So that bulky leaving group is gone and we get our alkene. Okay, so that's how you would predict that from the outset. Okay, so that's how it's a way you can get an amine to be gone. You can over-alkylate it, do an elimination, and turn it into an alkene. So you can turn an amine into an alkene, right? So that's something to keep in mind for your roadmap. So we didn't have that path before. What else do we need to know for a good, robust roadmap to be complete with amines? We need to know how to make them. So the most straightforward and simplest looking way to make an amine would be to be very careful with your stoichiometry and throw in just the right amount of ammonia to do an SN2. Okay, but here's the problem. Even if you control the stoichiometry, once you make your amine, the amine can attack the new amine, the brand new amine, the one you just put here. Instead of ammonia, the new amine, the alkylamine, can attack another one of these equivalents of starting material. And instead of getting only that primary amine, which might have been your goal, it tends to over-alkylate, even with stoichiometric attention. In fact, that'll just make it a mess. So unless your goal was to over-alkylate, it's not a good way to do it. So it's very difficult to control. So if you wanted to over-alkylate and form the trialkylamine, fine. But if you didn't, then there is another method with much higher level of control called the Gabriel synthesis to make primary amines, which requires blocking the two sites that would get over-alkylated with this fancier ring structure called succinimide. So you need to be able to recognize that, draw it, start with it. So what does it look like? It's a benzene ring with a fused 5-membered ring with an amide at the opposite end, right? But it's flanked by 2 carbonyls. It's called succinimide. What are we using succinimide for? We're using it to kind of block, like a blocking group, to block these sites so that only the H gets taken off and replaced with the desired R group. Right, so here's our desired R group. It ends up right there. Then you remove the succinimide. So how does the 6-cinnamon come off? You take advantage of amide hydrolysis, which we've done before. So that mechanism will do the part that's new. Let's work on that. Okay, so step 1, simple, acid base. We let the amine act as the amide really, act as a acid to the base that's added. So we'll have a lone pair that comes and deprotonates. So we have a negatively charged nitrogen that's much more nucleophilic now. It's actually resonance stabilized though, so it's a pretty, that's sometimes hard to make the nitrogen anions, but because this is resonance stabilized, it actually works quite nicely. Now, let's throw in our substrate. Let's see, the propyl bromide. So this is none other than an SN2. So that's why we like a primary or secondary. That's the only really restriction. But you could have backside attack and inversion. So if you see a stereocenter, watch out for that. Okay, so now we have basically done what we set out to do. We've put the R group on the amine only one time. That part's done. The rest is to hydrolyze the amide on each side. So because we have discussed that mechanism, I will refer you back to that so that we don't spend all our precious lecture time redrawing that. So, but you do it twice, right? Because you have to do each side. So you'll hydrolyze it and you'll get an amide on one side and amide on, and then you'll hydrolyze that one. So what happens when you hydrolyze an amide? What's the product? Carboxylic acid. So what if it's technically a diamide, right? A diacid would be your product. So this is the byproduct. So you get this diacid coming out. So that's the mask leaving that was blocking the other sites for us, so thank you. And now we have our desired amine with the R group, primary amine with the R group intact. So you will be needing to use the Gabriel synthesis when you want to make a primary amine because the obvious SN2 path doesn't work so well. In fact, we used it to overalkylate on purpose, right, for the Hofmann elimination. Okay, so that's a new reaction, the Gabriel synthesis. I'm going to bring up, since we're in the amine section, bring up some old ones so that you just want to be familiar with. So we've talked about how to turn a nitro group into an amine. So I'm just going to write the words so that we can kind of connect that in our brain, that we know that transformation. This went to the other page, reduction of amides. We know that one too, so I would encourage you to review the mechanism. But what happens when we reduce an amide? We get the amine. So we can start with an amide, and we can end with an amine. So your roadmap's already partially established. So these are things, when you put your amine in the middle, put these things you know in there first, just as review, and then kind of go back and fill in maybe the new ones to study them. We also learned that nitriles get reduced to amines. And so you can practice the mechanism if you like, but once again, I won't redraw it here. And I am going to go over this one in a little more detail because although we know about sodium borohydride and that we can reduce imines, we haven't looked at sodium cyanoborohydride as much. So remember, to get an imine, we can actually start with an amine. So we would start with, for this particular amine, we would have had, remember that's at equilibrium, we would have had this ketone plus the R double prime was part of the amine. So we had a primary amine and a ketone. Okay, so that's where we started. Eventually got to an imine. But you can turn an imine back into an amine, but it's not the same amine anymore. Look at the substitution. It's got 2 R groups, so it's a secondary amine now. Okay. So when you start by forming the amine from an aldehyde or ketone, and then you throw in the sodium cyanoborohydride, NaBH3CN, we call this reductive amination. So you might say, why can't we use, like, what's with this funky new reducing agent? I know about sodium borohydride. Why do I need to know about sodium cyanoborohydride? Well, it's actually a lot less reactive thanks to, notice that what's happened, you've replaced one of the hydrides with a cyano group, nitrile group. So it won't reduce the carbonyl, okay, but it'll reduce the imine because it's less reactive. So why is that important? Let me write that down first. Less reactive than NABH4. What is less reactive? Let's put that in front. NABH3CN. Less reactive than NABH4. Therefore, it has been found to not reduce carbonyls. You say, wait a minute, there's not a carbonyl there. Well, there was in the beginning. And the problem with isolating an imine to start the reaction is that imines are not particularly stable. They're really prone to that reverse reaction. So as long as it can go to that reverse reaction and we see that carbonyl, sodium borohydride would reduce it. So to keep us going forward, if that's what the product that we want, if we use something that's less reactive, we fine tune it just so it only reacts with that, but not that. That's its preference. So in that scenario, we're allowed to do this actually in one pot, which is very valuable. So I'm going to write that out and then I'll show you what I mean by one pot. So can make amines in one pot by adding the aldehyde or ketone plus your RNH2 plus sodium borohydride all together. Isn't that convenient? So notice how I made it look stepwise here, because this reaction happens, and you can do this when you isolate the amine, but you don't even have to wait and isolate it and clean it up. You could say, let's go a step back, throw these all together in one pot. It'll go through the amine, which will subsequently be reduced by this. So this just hangs out until the amine forms. That's pretty nice. So it's less reactive, which is why we can afford to have that product solvent too, right? So for example, here's that one pot reductive amination. Everything's over the arrow all at once. We're starting with an aldehyde. Our source of nitrogen is here. And we know from analogy what we should make. We're going to make the corresponding amine, because it's got reduced. They made an amine first, then an amine, with the R group that's designated over the arrow. So my aldehyde had one carbon, nothing else nearby, but my new group is an amine. And don't forget about that carbon right here. So I don't want to add the nitrogen there. N and a methyl and an H. Okay, so this is reductive amination. This combination of reagents. Not animation, amination. Amine. Okay. Let's do the mechanism. All right, so what's going to happen first? We will do the amine bond formation. So this is good review. It's actually things we know, but since it's put together in a new way for the first time, let's go ahead and do that. I'm going to call that benzene ring pH just to save a little space. Oh, it's not really phenyl because it has the methyl on it, so I'll just call it R. I'll call it aryl actually. That's another way you could do it when it's not actually just a benzene ring. So there's my aryl group. The aldehyde got attacked and opened. We're in basic conditions, so it's going to stay like that. And we have an H here still. So we've done the amine bond formation in acidic or acid catalyzed conditions. So this is how we would draw the mechanism with no acid present. So we don't the only difference is you just don't activate first. So we need to do an H+ transfer. Why do we need to do that? We know that we have to get that oxygen to leave. And the only way to do that is to gradually make it a more decent leaving group. But in basic conditions, that'll be OH, not water. So we have OH, N, and so we've likewise, oops, that was a plus, likewise neutralized that nitrogen, so that was a nice exchange. And close, kick, so that we have the imine bond. So we have our, I'll draw it with the same orientation. So the nitrogen's gone, excuse me, the oxygen's gone. So we're getting closer, but we have a positive charge here. Okay, now remember there's also an H on there, which kind of got moved to the other side there, or trigonal planar. So that's an imine. We can neutralize that. We have ethanol around. I'm going a little, I should have probably started off a little farther to the left because this isn't the shortest mechanism, but ethanol can come and neutralize that. Okay, we finally have our neutral imine intermediate. So I'll put little brackets around it. This is what we had started with over the arrow. I'll move that out of my way. Over the arrow, excuse me, in front of the arrow before we did the reduction. So we know that it could be reduced, but let's show that. Okay, so here comes our sodium cyano-borohydride. Now, one of those H's is going to attack new H, right? It's a new H. Open. I'm going to track that new H just because it's good to know. Like, what if it was a deuterium, right? So the green will help us do a problem like that if we ever see a deuterium. I'm going to start coming back home because I know that that's kind of going off the margin there. So I'm going to start drawing it out too because we're getting close. Okay, so we have our aryl group. We have our old H. We have our new H. Hello, green H. And we have our negatively charged nitrogen. So of course it's not going to stay that way. It's going to be neutralized. Ethanol's around to do that again. So that's why it's actually favorable to have a protic solvent. So we deprotonate and voila, we have our amine. Now, just observe some of our new groups. I wrote it out the standard way here, but our old H is here, our new green H is still there. And then if you want to say the red H, you know, from here, that would actually be from the ethanol, right? So I'm going to spell that out with filling those all in so you could kind of keep track of them in the mechanism as you review it. So we had our red H here, and our old H stayed unlabeled, and our green H was added to the carbon. So this H came from the hydride reducing agent, hence that's why it's attacked a carbon that used to be part of an amine. This was simply an acid-base reaction, so it came from our protic solvent. Very cool reaction because it's very convenient. You can start with an aldehyde and go to an amine in one step. So that's very useful. Amines are very useful. Okay. Oh boy, you might want to sit for this one. This is cool, but it's going to be a long mechanism. So I wonder if I should take a break. How long have I been going? Yeah, I'm going to take a break. But what I'm going to show, what I want you to think about to warm up for this, our starting material. Look at what we got. We have an amide, right? Amide, amide. So I'm going to draw this again up here, just a little generically. So we have an amide. All right, and what do we do to the amide? The amide is now an amine. And you might say, oh, no big deal. We've done this before, right? We've turned amides into amines. How did we do that? We did that with LAH. You are right if you're thinking that. We did do that. So why would we need a complicated rearrangement to turn an amide into an amine? So I'm going to show, we're going to compare those side by side. Just for review's sake, draw this product. What happens when you turn an amide into an amine? To neutral, oh, we can even neutralize with water. Let's do that. Versus the Hofmann situation. Cl2, O minus. This is a Hofmann rearrangement. It's not elimination. So I don't expect you to draw this yet unless you try to do it by analogy. Look at what happened to the amine, okay? How is that different than if I did LAH? So I want you to draw these products and then compare it to what's in the box so that we could predict this one, okay? So give that a try and then come right back. Okay, so what did you get? I hope you got this for your amine, right? Notice what happened here. We did not get that with this Hofmann rearrangement. We lost a carbon. I'm writing that in red with an exclamation point or 2 or 3. So in other words, we still get an amine minus a carbon. Where did that carbon go? That's why all these little byproducts are written out for you. There it is. So that is worthy of paying attention to this mechanism. But by analogy, let's go ahead and predict the product. So we say, okay, we know what happens. We know that when we start with an amide, we're going to get an amine with 1 less carbon. So let's draw that out. That means the carbonyl carbon is gone. And so is the oxygen. The whole carbonyl is gone. So this just went off as that carbonate eventually. Let's write that out. Something to explain all this. I'm going to call this pH for good reason. And I'm actually going to start on the margin. I'm going to get ready for this adventure. Give lots of space. Saying, oh no, here it comes. All right, so I'm going to start off with pH with my 2 R groups. I am drawing out the amide, of course, and all of its H's. We're going to start with a simple step, acid base. Okay, so I'll get us going. We have to work toward keeping the nitrogen, getting rid of the carbon and oxygen. So, but really with that base there, that's really all we can do at the moment. Okay, so now we have NH minus. Okay, so that is nucleophilic enough to attack chlorine. That's why the chlorine's there. So remember that chlorine itself is nonpolar, but when it approaches another molecule that's got a polar region or ionized, it can induce a dipole. So that'll, in this region, that's exactly what will happen. We'll get a delta plus as it approaches that negative charge. So there just happens to be around in solution, approaches it, you get a negative charge. The negative charge density is diffused away from it, repelled, where the concentration of negative charge is on the opposite end. So this gets a delta plus here, so that can be attracted to it. That explains this attack here. Attack, kickoff. What are we doing with that chlorine? Why would we do that? We don't have that in the product. You'll see. All right, so we have our nitrogen now has a chlorine and an H. We are going to, the base is still around, we're going to deprotonate again. You say, okay, fine, I'm doing this twice. Not really. We'll keep it interesting and do something different. So this part's the same, where we have a negatively charged nitrogen. Okay, so now we can actually do our rearrangement step. All right, so we can draw a resonance structure to delocalize that negative charge. We didn't do that before simply because our goal was not to delocalize the negative charge on the end, where our goal was to use it as a nucleophile. but it did exist before. Right now it's going to benefit us, so that's why we're showing it. How is it going to benefit us? So if I do this, I can explain what happens. And this is called a rearrangement, this whole reaction, the Hofmann rearrangement. So we're watching out for a rearrangement, and this is where it's going to happen. So this is where you want to look closely. Are you looking closely? Okay. So you're ready? All right, so what we're going to do is close this back down. And instead of kicking open the pi bond, we're going to kick off something else. This bond that we know is not attached to the oxygen carbon bond anymore. So lasso it, since it's a rearrangement, shifting. So it's close, kick that off. It's going to land on the next atom over. So it's a shift, basically. This closing just prompts it. As it lands on nitrogen, kick off the chlorine. So the chlorine was a leaving group for us, kind of keeping nitrogen happy until we had to attack it. We wanted something to leave when we attacked it, and the hydrogen just wouldn't do that. So that's why we replaced the hydrogen with the chlorine. This is really the whole aha moment of the mechanism. That's your rearrangement right there. That's the meat of it. So I'll write those in words, what happened. This is an alkyl migration. So a 1,2 alkyl shift, basically, as chlorine leaves. Let's draw out the consequence of that. What are those arrows telling me? Those arrows are telling me that the pH is still attached to that dimethyl group. However, that carbon that has the dimethyl is now attached directly to the N. So you've just broken that link right here. This link is not there anymore. It's now bonded here, but that nitrogen, it has no more chlorine, but it still has that double bond to this carbon. That was that carbonyl carbon, which has still got, well, now reformed its carbonyl. This is a neutral intermediate, and it has a name. It's called an isocyanate. When you have this functional group, that linear NCO in series. Okay, so you have the isocyanate, but we know that's not our final product. But look at what that did for us. We knew we had to have that carbonyl leave eventually, and that pushed it out to the edge. It's not in the middle of the molecule anymore. It's out on the edge. It's going to be easier to visualize how that's eventually going to be gone. We're going to make that happen. Okay, so now more hydroxide comes in. Why? We're working on making CO2. CO2 is the good leaving group for when we want a CO to leave. So we're working toward making CO2. Attack, open. So the way to do that is to get another bond to oxygen, right? And we have pH, N, C. And that C is opened up to an OH and an O minus. Okay, close. It's not going to kick off the OH. It's going to open that pi bond. So look at where we have what we have now. So we have N minus, and then we have our carboxylic acid. We're going to neutralize that to get to another neutral intermediate. We have water present. Even water will be something we can use to help us with that. Okay, that is neutral. So most of our neutral intermediates have a name. This is called a carbamic acid. Carbamic. It's a carboxylic acid that has an amide on the functionality on the other side. So one side looks like carboxylic acid, the other side looks like amide. It's like Jekyll Hyde. Carbamic acid, so it's a difunctional sort of group. Okay, so it doesn't stay there though. We're in basic conditions, so it quickly gets deprotonated. So like I've said, a lot of these steps are simple, but plentiful, but we are trying to, get to the meat of it, which was how did that rearrangement happen? Okay, so we form our carboxylate. Okay, now why did we do that? Because CO2 has no H, it's not carboxylic acid, and we want CO2 to leave. And that's exactly what we're doing. Are you ready? This is the fun part, another fun one. Close. There's our CO2, but it's got to detach from the nitrogen right there. All right, so we have our pH back home, NH minus, and CO2 gas, which I have to draw the squiggly arrow just to reward myself for doing that. We're basically there, just another proton transfer. So we wrote out every little detailed step here, so why stop now? So here we go. Sometimes it's good to have the easy things mixed in with the hard, right? Just give your brain a break. So that's how you do a Hofmann rearrangement. It's not the cracks beneath the floor, it's not the fact that it's a chore. It's the nature of the experiment, it's the pattern for man. Are you ready for the SNAR sequel? Nucleophilic aromatic substitution? Well, look at what we are going to do here. We are going to have this little roadmap ready to go, and you are going to have a leaving group that is so good that when you add water to benzene with this leaving group on it, it reacts. Water. So that is a weak nucleophile. And how does it react? You replace that N2 plus, a diazonium salt, diazonium, with an OH. You get phenol. That's a direct path there. So with water. So that's actually, and so we'll fill out the rest of this as we go, but I kind of wanted to highlight the importance of what we're about to do, because we don't just start with this. Why is it in the amines chapter? In other words, why is that here? We don't just start with azonium. We have to make it from an amine. So you get like an aniline derivative, and then you convert it to the diazonium. Then bingo, the diazonium opens up this pathway of the diazonium 6. That sounds like a band name. So that's our goal. So this is a SNAR reaction essentially. So how do we make the diazonium? So we're going to show that on the previous page. An important leaving group. So if you want to use a weak nucleophile with substitution, right? SNAR type substitution, then you need a good leaving group. Diazonium, why is it such a great leaving group? Look what happens. We've used it before in SN2. Look what happens when it leaves. Yes, we will have a carbocation, but we just liberate an N2 gas, right? So that's why it's such an easy reaction to do. But we have to make it first. So here's the synthesis. You need something to add your additional nitrogen. So you start with an amine, and your source of the nitrogen is the sodium nitrite. And that's to get your azonium, diazonium. How does that work? Well, it's a series of, the HCl plays a role too. So of course, since amines are basic, that's the first thing we might consider doing is protonating that. And that would actually be okay to do, but that's going to mess us up if we start there. Because what actually happens before is the diazonium is getting prepared as a, let's write this out. So although the amine is basic, remember this is an ionic bond, Na plus NO2 minus. So what does that mean? That means that if we write out NO2 minus, we can see easily how that would react with HCl. So we have that going on. And in fact, it could keep reacting. So we have our OH here can actually get even more because we're in acidic conditions now. And why did I do that? Because I don't have an oxygen in my product. I'm not adding oxygen. So I'm trying to get to a point where I'm allowed to use this nitrogen and close to only it. So we can have this OH2. So I'm making a water leaving group, good leaving group, and we're going to let it leave. Why are we doing that? We're going to get this reactive intermediate that the amine, here comes our amine. Your starting amine can come and attack. That's kind of the big moment there. We made our nitrogen-nitrogen bond. We introduced that nitrogen into the parent compound. Okay, draw this out now. R, N with H's still attached. New bond to N, double bond to O, positive because that was a neutral amine that we started with. Okay, we're just going to kind of take care of the neutralization business here. So I'm just going to write minus H plus. So we're not belaboring that too much. Okay, we need to get that O out of there and make triple bond between the two ends. We also need to get the H out of there. So we'll use HCl to facilitate that. So HCl will help us get the O. We're going to gradually work toward getting that oxygen to leave. So protonate it. I mean, you got it. You can't just have that carbonyl, or it looks like a carbonyl, and then the N double bond O disappear. So we're going to have that essentially activated, if you will. Activated for what? What's coming next? All right, so we have the chloride sitting around from the HCl, and it can take that H to make more HCl and eliminate. That's nice. We go from a single bond end to a double bond end. Remember, we're working to a triple bond end, so that helps our cause, and open. So we activated that so that we could attack two atoms down, eliminate, and open, right? Okay, so now it wanted to open. That's what helped facilitate that reaction. So what do we have? We're at a neutral intermediate, but we're not done. So some more HCl comes along. And you guessed it, no longer a carbonyl. That means we could form water. Water, our favorite leaving group, right? So while we're at it, let's push all those arrows. Form our triple bond to expel the water. And where are we? Here we go. R, N, N, and that's the positive charge there. Bingo, diazonium ion with a great leaving group ready to do substitutions on that R group, okay? So the one that we'll be using it for the most is the diazonium 6, because that's a big deal to be able to add to the benzene ring. So you have to start with aniline. Remember, aniline got you there. So I'm just gonna put a little reminder of that here. Let's fill that in. So you have to start with aniline to get there. But what do you add over the arrow? Do you remember? Let's look back if you forgot. NaNO2 HCl. Okay, so start with aniline, get to the diazonium. Then once you get to the diazonium, you could do these 6 reactions. You can have a fluorine. We didn't have that before, get on there, HBF4. You can also add a halogen, which we have done. This is just another way. So if you see the copper halide, so either chlorine or bromine, that's a sign that you did that with the diazonium ion. So I'll put X. But you could also get iodine on there, and that's another one we haven't used before for the specific halogens. You could get a nitrile on there. And then you can also take it off, just have plain old benzene. So why would we do that? We're going through all this trouble to react benzene. Why would we take that off? Well, H3PO2 can remove that. However, maybe we start with aniline and we want that aniline, the amine part, to be gone. So that's why we would go through this path. Okay, so in terms of mechanisms, you're not responsible for these, just consequences, okay? Anything I wrote out we're responsible for, but I'm not writing out all these mechanisms in great detail. So, there's kind of enough here as it is. So we've kind of done our due diligence with electrophilic aromatic substitution and nucleophilic aromatic substitution. So this is just kind of a icing on the cake with more that we could do with it, okay? But it's a good reminder to go back and review, because we can start making molecules from benzene with many more options. So it would be a good idea to practice a synthesis. I actually have a few here for you to do. So I want you to try those. So you can make the tribromide. You could also make the meta-chlorophenol. So what are some options? Think about that. Well, this is an ortho-para director, so you want to start thinking that way, right? It's an ortho-para director, remember that? But so is this, ortho-para. So what should we do? It turns out that in order to start from benzene, if we were going to do any of the diazonium-6, we had to pass through aniline. How do we get aniline? Aniline's still ortho-para director. That doesn't help you, right? The amine on there. But you get aniline from nitration. There's your meta director. So you need the meta director. This is more of a mystery. You didn't have something obvious. I'd avoid using the diazonium as a director just because it's so reactive. So if you put anything in the presence of it, it's going to kick off too easily. So don't worry about its directing abilities. Focus more on the directing abilities of those more stable species. So the fact that you know that in order to ever arrive here, you had to have one path, especially if you consider what we just did, would be to go through aniline. The only way to get aniline is through nitro. Nitro is a meta director. Okay, so let's write that out. Let's see, N2, which came from N2 plus, which came from NH2, which came from nitro. And then finally, we have our meta director. So that's your clue. I want you to try this now that you have kind of unlocked that secret to it, and use our new reaction. I know we have other ways to get an OH on there, but I want you to use our new reaction to direct where it's going to go. Okay. Now, once you feel good about that, go ahead and give that a try, and we can check our answers together.